Hello, this is Paul from Foresight Tech. In this video, we are going to deal with the linear approximation, which is a method we can use to approximate the value of a function at a particular point. Okay, let's see the material. First, I will introduce the method of a linear approximation, or we also call the linearization. Then we will practice just one questions together about how to use the method to do approximation. And let's see. So here is the definition. Okay, so we can see. So we go to linearization first. What does a linearization of a function at a? Okay, is let's look at this graph. And first we have a function. If the function is differentiable at this point at x equals a, which means what? Okay, which means the function should be very smooth around this point, right? Therefore, if we zoom in, imagine if we just zoom in and zoom in and zoom in at this point. Okay, so finally the curve around this point, the original curve, okay, should be looks very like a linear function, like a straight line. What that the straight line? Of course, that's the tangent line, definitely. And the tangent line, we set up y equals lnx. So the lnx we call the linearization, which means what? Which means if we zoom in and for the curve just around this point, we can do approximation just use the tangent line. So that's why we call the linearization. Okay, so here we give the tangent line equation. Okay, so why the tangent line equation look like that? Let's going to just have a look. Okay, so I'm going to get the tangent line equation, which is easy because what? Because we know the point, we know the slope, which is just the derivative, right? So we can use what? We can use the point slope. Okay, so we can use the point slope to get the tangent line. Let me put here the point slope form. Okay, so you know this should be y minus y0. Y0 is f at a, right? So f at a equals m, which is the slope. The slope is derivative at a, right? Times parenthesis x minus x0. X0 is a, because we look at this point. Can you see? Of course. And then I plus f both sides, and then we can solve for y. And what is y? So y now equals this f at a plus f prime at a times x minus a. Can you see? And this is just the let me put the arrow. This is the tangent line, right? Okay, so this is just the tangent line. Can we look at here? Okay, so now this tangent line we set up as a function Lx. This Lx is just the linearization, right? So the formula there. Now the second, we just said we can use the Lx to approximate the original curve just around a, which means a linear approximation. Can you see here? What does that mean? If x is near a, just around, okay, and then fx can be approximated by this linear function. This linear function exactly is Lx, which is the tangent line, right? Okay, therefore this we call what? We can use the tangent line to approximate the original curve around a. Why this is true? Okay, so let me just show you on the graph so we can see it clearly. What does this really mean? I will draw a little bit. Can you see here? So first, let me get this out. Okay, so first, where's a? A is at here, right? I'm going to get a, and this is a. Where's x? X is near a. Let me just around here is okay. Draw a vertical line. I said this is x. Okay, a little bit far, but I just say x is just near A. Now, what do we have? We have a 2 point. See, this 1 point is on the original curve. And we have the second point is this point. Okay, can you see I'm drawing? Okay, so this point is on the linearization on the tangent line. Can you see these 2 points? Can you see these 2 points is very close, right? 2 points are very close to each other. Therefore, we can use the red one, which is LX, to approximate the green one, the height. Let me show you what is the height. Okay, the height is just like this. How high is this one? Okay, so I draw a little bit like this. Okay, I get up a little bit. No, I will. Okay, so this one is not easy to get. Let me just draw a small line. I will show you how high. Okay, is fx. Where is fx? Okay, fx is here. Okay, so from here to here, right? And then is from here to here. We can see. Okay, so in the middle, this is fx. Is this right? Okay, which means the y coordinate of this point, that's on the original curve, which is fx. Now we have another. Okay, the red point, can you see? Okay, exactly, we have this term, and this is how high is the point on the LX, which is LX. Of course, we can see now we can do approximation. F can be approximated by LX. That doesn't make sense. If I write it down, it's like this. Okay, and Fx is approximated by LX. Okay, from the graph, it's easy to have a look, right? Because what? Because these 2 points are very close to each other. Okay, if we put the LNX, okay, which is there, into here, that's what we call the linear approximation. And because what? Because the right side is just a linear function. The left side is what kind of function is okay. Okay, just the differentiable at the point that is. Another understand, which is even more important. Can you see here? If we need to approximate fx, which means we're going to approximate or estimate the value of the function at a point x. See, the right side, all we need is the value or the value of the function at the point A, or the derivative of the function at A, which means what? We only need the basic information of the function at this point. Okay, can you see? So how amazing. If we have the information of the function around this point, and then we use that information and the linearization, we can do approximation for the value of the function just near A. Okay, so which means what? We can get the new information just from the point A. Okay, so now let's going to work on one question. So you will find out how amazing it is. We can use this to do approximation. Here is the question. What do we do? Square root of 100.5. Okay, this is a square root. If we don't have a calculator with us, so it's so hard to get the square root, right? Okay, but we just learned a linear approximation. Imagine, okay, if this is a square root of 100, we know the we know the value, which is 10, right? And the 100.5 is just near 100. Do you remember we just say linear approximation? We can use the information of the function around the point A, and to approximate the value of the function around A. Okay, is exactly this type of questions. Let me going to show something. So what is the function? Of course, is square root of the function, right? Let me going to define the function first, and then I will going to use the linear approximation get the answer. So the first, let me set up fx is this. square root function. Of course, I will change a little bit. I will use x plus x, 100 plus x. Of course, then if x is 0.5, then this, right? It's the same. If you want to use square root of x, of course, it's still similar. But we need to change a little bit. Now, we will have this. We will have what we need to find. 100.5 take square root is just evaluate the function at 0.5. That is true. Okay, so now can you see? And this is just we're going to do evaluation at f, right? All we need is use another point. What is another point? Of course, we're going to show you, okay, to show you what the linear approximation. I will show the formula here first. And then you can see exactly what? Exactly this function, we can do approximation at x equals 0 because 0.5 is close to 0. Okay, and all the other information at 0 is available for us. If I write this, you will see this is definitely true. The linear approximation is this formula, which is fx can be approximated by f at a plus f prime at a, right, times x minus a. Right, is this true? Yes. In our questions here, what is x? 0.5. Let me put here. So we need to evaluate f at 0.5, which means x is 0.5. Which a we can choose? I just should is 0 because 0.5 is close to 0. And also f at 0, the derivative at 0 is easy to find. Okay, so I will say this is I will choose a is 0. Okay, so here is 0. Can we see? Okay, so the derivative at 0, of course, we can evaluate later easily. So x minus a we also know is 0.5 minus a, right? And then I will get this form. See, I will change it to f at 0.5 now can be approximated by f at 0 plus f prime at 0 times what? X is 0.5 minus a is 0. Okay, so this we call the linear approximation for f at 0.5. Can you see? All we need is the information at 0. And this we can do, and also do this. If we find these two information per log in, we find the approximation. Does this make sense? Therefore, tell yourself, so this is the most important equation. Okay, so we need to use. Now, I just evaluate. Everything now is easy. Okay, if you set up this one, what is f at 0? We're going to find f at 0. F at 0 is square root of 100 plus x is 0. Of course, square root of 100 is 10, right? The second, we're going to find the derivative at 0. We're going to find the derivative function first. Okay, so f prime at x is what? The function, if you remember, is this we defined is 100 plus x, right? Take the value, okay, equals what? This is a chain rule, can you see? And this is a composite function. We have to use a chain rule, okay? The inner function u is 100 plus x, so the outer is square root of u. However, the inner function take a derivative is just 1, right? Therefore, what we left is only the derivative of the outer. Okay, the outer, you remember that we did a lot of times before, is this. Okay, is what? Is 1 over 2 times the square root of u. Okay, square root of u, u is 100 plus x. Okay, is this true? And if you find this is chain rule, let me just put here is remind you this is chain rule we used. Okay, now we can find out what is the derivative at 0, right? Okay, so the derivative at 0 equals this 1 over 2 times the square root of 100 plus 0 is 1 over 20, right? Okay, now everything is set up. Okay, I'll plug back to this formula. Okay, and then we will get what we need. So we have this f at 0.5 exactly is this, is 100.5. okay, so this is f at 0.5 and approximated by this. And what is f0? We're going to plug back. f0 is 10. Okay, and then plus what's the f prime? We just find it is 1 over 20, right? And then times 0.5 minus 0 is 0.5. Okay, so this is easy to do calculation. You calculate, you don't need your calculator, right? Easy to do calculation. You get a 10.025. See, this is the final approximation. And these for these questions, if you have a calculator, please going to verify. Okay, use a calculator to calculation. See how good is this approximation. Accurate at least 2-3 decimal places. Okay, we do not need a calculator in this method. And this all about this topic. Thank you so much. If you have questions about this topic, please leave your comments. If you like this video, please give me a thumbs up. And you are very welcome to subscribe to my channel for more videos. Thank you for your support. In the next video, let's see. We are going to deal with this differential. Okay, what is differential? Which is a concept related to linear approximation we learned in this video. Hope to see you there. Thank you. Have a nice day. Bye.